Okay, we're going to work on sample problem 12.1, finding the heat of a phase change as depicted by a molecular scene. So sometimes you might be provided a picture that kind of describes what's going on. Sometimes it might just be in words. Sometimes in this case there's a combination of both. Pictures, again, we have to kind of discern and look at this, and again understanding that it's water. At 85 degrees, this again is representing a liquid. And we can see that for liquids, you know, our molecules are close together, but they're not very well ordered. And then over here, we can see that we have a gas, and that's expected if we're at 117 degrees. We've already boiled at water. So it wasn't part of the problem, but I had kind of indicated to draw a corresponding heat and cooling curve. And I always like to do this because looking at a picture will kind of help identify the parts of this process that we're undergoing. So, for example, I think you should always have in the back of your mind what a typical heating or cooling curve looks like. Again, we're heating this substance, so we're going in the forward direction. For cooling a substance, we could just draw it as the opposite. So what I want you to have in your mind is thinking that for any solid, we have the ability to heat a solid until it reaches its melting point. And then when we reach that melting point, again, now heat is used to melt that solid into a liquid. And then again, we're going to heat that liquid until it gets to its boiling point. And then further heat applied is going to vaporize that substance. Remember, the freezing or melting transition is always going to take less energy than the vaporization transition. And then once all of that liquid has been vaporized, then we can begin to superheat the gaseous phase. And so we need to figure out for any of these problems which area we are here. And so that's why I have you draw a corresponding heat and cooling curve. I'm never going to be able to give you a problem where I assign you the entire, transition here. That just would be way too many calculations. Also, for water, it's assumed that you understand that 0 degrees is the melting or freezing point, and that 100 degrees is going to be the boiling point, or again, the point for condensation of vapor. If it is a substance other than water, I would have to give you those values. And again, other values that you would be given are the specific heat capacities for the solid, liquid, and gas phase, as well as the enthalpies for fusion, and again that has to do with melting or freezing something, and then the enthalpy of vaporization, so for boiling or condensing a substance, again depending on which direction that you're going. Okay, so a little bit of a review qualitatively about a heating or cooling curve. So we just kind of have to figure out for this problem which region of this that we're in between. And because we know it's water, we can see that we start here at 85. So we're going to be starting kind of right here on this plot. Then we're going to have to go 15 degrees to heat that liquid to get to its boiling point. Then we will boil all of the liquid that's there. And then again, once we get all of the molecules in the gaseous phase, we will continue to heat that steam until we get to 117 degrees. So this tells us that we're actually going to have 3 calculations that we do in order to figure out the answer to this problem. So let's kind of call these an A, a B, and a C calculation. And remember that there's basically 2 kinds of calculations. There's vertical transitions, which we see for A and C here, and horizontal transitions, which we see for B. So for vertical transitions, that's where we're heating a substance that's in the same phase and changing its temperature. We use the same equation, and that equation is that the heat is going to be equal to the specific capacity, and we have to make sure we match the specific capacity for the phase that we're in. So for A, that's a liquid, so we'll use this. And then for C, that's a gas, so we'll use this. I'll always give you all of the information, probably on a quiz or an exam on the front page there. So it'll be something that you'll just have to know which parameter to grab. So the heat is going to be equal to the specific capacity times the mass times what temperature are you changing. And a common mistake that students make is they'll subtract 117 or 85 from 117, and they'll use that value here. But remember that that's not what's happening. We're not changing the temperature of a liquid from 85 to 117. The liquid changes from 85 to 100, and then the gas changes from 100 to 117. So again, make sure that you have the correct delta T there. And again, if we see the units here are going to be Kelvin. But remember, when you're taking the difference of temperatures, the difference between 117 Celsius and 100 Celsius, which is 17 degrees Celsius, is the same as if it would be Kelvin. Because really you'd be just adding 273 to both of those numbers prior to subtracting them, and that difference just kind of ends up not mattering. So when you're looking at the difference in temperatures, Kelvin and Celsius is the same. So this again is going to be the calculation or the equation that we use for the A and the C. For the B, we need to use something different. And again, I should have mentioned here that the mass of your substance, that's going to be 24.3 grams of water. And we're given that directly, so those calculations will be fairly straightforward. For any horizontal transitions, which we have one here, we have to match whether it's, again, a boiling or condensing, or a melting or freezing. And we're doing a boiling transition here. So we need to use the enthalpy of fusion. So all that you'll do is you'll take the enthalpy of fusion. That's a constant, saying that it will take 6.01 kilojoules for every mole of substance that we have. We have 24.3 grams of water. We can use the molecular weight to convert that into the number of moles. And essentially then we just need to scale this value up or down depending on whether we are greater than or less than a mole. And as we talked about in class, this is going to be more than a mole because the molecular weight of water is 18.01 grams per mole. And we also have to keep in mind that the answer that we'll get here will be in joules. Here will be in kilojoules, so we'll need to convert into the same units before we add them together. So that's a little bit of a setup for this problem. So let's go ahead and solve these three areas. Since I've already got this equation set up right here, and this is going to be for the B, let's go ahead and just solve that portion first. Again, it doesn't matter which one that you solve here first. The first thing in the end we need to get is the number of moles of water. So to figure out the number of moles of water, we can take the mass that we have, which is 24.3 grams of water. Molecular weight of water is 18.01 grams of water, is 1 mole of water. And we work out this calculation and we get 1.349 moles of water. So what that really means, then again, delta H of fusion equals 6.01 kilojoules per mole. And when we multiply that, let me write this out like this. Kilojoules per mole times 1.349 moles. Now we're going to end up getting 54.874 kilojoules, right? Because moles are going to cancel. I encourage you to keep lots of significant figures early on here as we're working through. We'll reconcile significant figures at the end, but you don't want to round too soon because that can end up having you lose accuracy. So keep lots of significant figures early on, and at the end make sure to round your answer to the right number of significant figures, and it might be that you're not quite certain, so I always give you plus or minus 1 significant figure. All right, so this is the answer for B. So let's go ahead and figure out the A and the C. So let's start with A. Again, we use the equation Q equals C times M times delta T. For the A transition, again, that's heating water as in a liquid form. So we have to make sure to use the liquid specific heat capacity, so 4.18 joules per gram Kelvin. We know the mass of water is 24.3 grams. And we know that the delta T, the change in temperature, and we can just kind of do this one in our head, 85 to 100 is going to be 15 Kelvin. And remember, again, that's also 15 Celsius, but the increment is going to be the same whether you're in Kelvin or Celsius. So, doing this math here, we end up getting 1523.61 joules. And reminding ourselves, we've got kilojoules here and joules, so we'll have to remedy this before we can add these together. Similar calculation here. Oops, this is going to be for C. Q equals C times N times delta T. Now the C transition is for the heating of water in the gas phase, so we have to use this specific heat capacity. We still have the same amount of water, it's 24.3 grams. And this time we're going from 100 to 117, so that's going to be 17 Kelvin units that we change. Okay, go ahead and do that math, and we get 760.104 joules. So the overall heat, so the heat total equals the heat that we have from the A leg plus the heat for the B leg plus the heat for the C leg. So we add all these up. Again, we need to make sure that we have everything in the correct units. Whether you change the kilojoules into joules or the joules into kilojoules, it really does not matter. I'm just going to show here that I changed everything into kilojoules. So 1.5236 kilojoules plus 54.874 kilojoules plus 0.7601 kilojoules equals 57.158 kilojoules. And again, looking up here, the only value that's given to us that we can derive significant figures from is the mass of water. Everything else is a constant. We don't use these for significant figures. And so 24.3 means we need to have 3 significant digits in our answer. So rounding this, we're going to get 57.2 kilojoules. I always encourage you, box your answers. It's an easy way to let me know where to look for your answer. And always show as much work as possible, because it's very easy, particularly with problems like this, to make a silly math mistake. But if I can follow your logic and I can see where you were going, it's very easy to assign the most partial credit in that way. Just a couple of other comments. You will see a problem like this likely on a quiz and on an exam. There's lots of ways that I can make different permutations of this problem. This one happens to be heating, so in this case Q is going to be a positive value. If you were cooling, that would mean that heat would be given off, so this would end up being negative. And that's not anything that you'd lose a lot of points if that was not correct. But just remember that these are reversible processes, heat being put in, heat being lost. Other ways that I can permute this problem, again, just give you a different region on this whole transition that you'd be looking at. Give you a different substance. So water is a pretty easy substance to think about, but I can give you a variety of other substances as long as you know what the substance is, so you can figure out the molecular weight, as long as you know the constants for the specific heat capacities of 3 phases, as well as the enthalpies for the 2 phase changes. All of those will allow me to kind of make lots of different permutations of this problem.